There we go. All right. So we're up and running. A quick discussion on what we've been discussing right along. Cubics. Lots to still analyze. And when I say lots, I mean lots, and it never stops. That process never stops. Because as you keep doing things, you see little nuances that you didn't see before. Big screen here. All right. So what's a graphing form? This out of the way for now. I got a marker. Yeah, I got a marker. All right, so that's a graphing form. That's the first one you probably encountered back in Algebra 1. So what are we doing when we talk about graphing forms? Adding up different terms. So this is about the easiest one we can probably work with. What happens when you add those two graphs together? What do you get? And why? That's what we're talking about now. And we're trying to get to the cubic, which is more complicated. But if we understand the steps in getting there, maybe it won't be. That's our goal for the first little chat. So what happens when I add those two graphs together? Anybody? I add the y values. And I add the rates of change. So how is the dotted line changing?
Changing x.
The x is changed, true, but that we basically call those the independent variables. In other words, you're just using numbers. When you put an x value in an equation, you pick any x value you want, and you use it. The real issue is what happens to it? What happens to that number? How does it change? And I'm suggesting that you get that as a result. So how would you say your results are changing for the dotted line? Think of the y values on the dotted line.
Constant.
They're staying the same. So they're not changing. So we refer to a horizontal line as a constant, and all it does is adjust your graphs vertically. Whereas these y values right here are negative, these y values are positive, but when I add the two graphs together, it simply does what to the linear function? Moves it up. So every single value here goes up. So that value there goes up that amount. So you might have something that looks like that. This y value goes up that amount. And you might have something like that. And what's created is hopefully a marker that works better. If I got one, maybe this one will be a little darker here. Yeah, that's a little better. And so what do we get? We get a screen that is now centered. I think that might mean more to you when I write something that agrees with what I'm looking at pictorially. Now, you probably would have gone to y equals 3 and gone up at a 2-to-1 ratio, and that's what you learned in Algebra 1. I don't know if you considered it much in its parts from a graphical standpoint, and I'm asking you to, because each graph gets slightly more complicated. Okay, so hopefully we know what a constant does now. A constant simply shifts, and this is why they have this topic called transformations. I disagree with transformations in the sense that I think you have algorithmic change from a position, and you should measure it from that position and talk about it from that position versus saying, okay, we have the graph of y equals x. What have we done? We've doubled every value and shifted it. Fine. That has two terms. Graphing forms tend to try to blend certain graphs, and we can actually blend this graph and make it a one-term expression. That's one term. We don't do that for Algebra 1. Okay? We generally do the mx plus b, y. Everybody understands it. So everybody works with it. But the problem with it is you develop a linear mindset if that's all you look at. And that's what students have coming into Algebra 2, a linear mindset, which doesn't work too well when you start studying trigonometry, which isn't a linear process, or any of the other functions. All right, so that's a graphing form. If this had been What came your way? Well, then you got -3/2 and you're going up at 2 to 1. It's the same graph, but I'm only looking at one term. All right, so what happens when we get to the quadratic? It gets a little more complicated. We have an ax squared term, which could be positive or negative, could be cup shape up or down. I'm keeping it positive values here. Well, I didn't in this case. The x is decreasing, so b would be negative. And there's our constant. Okay, now if we've learned something from this, what can we say about the graph with respect to the constant? All of this activity shifts where? Down. So really, we can ignore that and say that, okay, maybe this is -5 now. Maybe we're looking at, all of that's happening at -5. Now we get a little interplay here. We've got two graphs we're adding, and they're both changing. And whereas we added two graphs over here, one was constant. Okay, we've dealt with the constant, we've moved things. So now the issue is what's happening. And we've begun to talk about rates of change, I think, haven't we? Right? Quadratic, the rate of change of a quadratic occurs when the geometry of the rectangle is what? Or square. I'm looking at square. So what's the area of the square that's most important? Said it probably 100 times this term. Can anybody tell me the size of the square that's most important?
0.
Absolutely. 0 is where not much change is occurring. Okay, the rate of change at 0. I mean, you can look at 0.0001 and square it, and you get 8 decimal places with a 1 at the end. Whereas we've looked at 4.001 and squared it. What do we get when we square 4? 16. What do we get when we square that? 16.008001. There's some significant change when we get past 0 squared. Not much change when I, do wherever I wrote it. Maybe I forgot where I wrote it. There's not much change there. Right? But when you start tacking on a coefficient bigger than 1, especially, you start to get a lot of change. And I hope we see lots of change versus no change. All right, so what's going to happen in terms of the rates? If I zoom in here right now, I think the rate is going to be determined by what? You got two graphs. Quadratic that's not changing and a linear function that is. If you add those two rates together, what do you get? The rate of the linear function. All right. So that means that if you were looking at 2x squared plus 5x plus 3, the first graph you're looking at is what? I hope 3. I hope you look at that and go, oh, wait a minute. Because if I put 0 in, I get 3 out. We've dealt with the constant. What's the graph going to look like? 2x squared. Okay. I think it's going to look like the linear aspect. And then what's going to happen after that? The quadratic term is going to add, starting to add more change. More change. So things are actually going to go up faster. Right there. So we have some kind of bottoming out on the left side. And when does that happen? Okay, well, this is starting to go up, yes. This is pulling down at the same rate. So it looks to me as though if we look at that y value and compare it to that y value, like a tug of war, small positive, bigger negative, who wins? Hope you see the negative. But at some point, I'm going up a lot faster. I'm pulling up a lot faster than I'm pulling down. So this function is going down, but eventually it's going to go back up again. The question is, when does it turn and why? When is that moment going to occur? Any answers? You're in a tug of war. You got a certain force this way, a stronger force this way, right? What's happening to the flag? It's going that way. But then people realize they're losing and they start to kick in, yes? So when will that stop going this way? When the other people start pulling just as hard. So where does that occur here? I don't know. Whenever I'm going down, the same time I start going up, alternate rates. Alternate rates. And that's where this thing's going to bottom out. So if you were given a particular problem that looks like black, okay, and black originally had a constant across here, yes? So what might that have been symbolically? Well, the quadratic could have been 2x squared. The linear term could have been minus 12x. Doesn't look like it's going down at 12 to 1, but it's going down. And the constant could have been something like minus 5. I think that's the example that I have in front of you. Yeah.
So what is BX doing? Is it affecting the thickness of the, like how thin or wide?
No, it's just a table of values where 0 gets me 0, 1 gets me minus 12, 2 gets me minus 24. At the same time over here, 0 gets you 0, 1 gets you 2, 2 gets you 8, 3 gets you what? 18. Over here, 3 gets you minus 36. Okay, what's the difference between minus 24 and minus 36? It's pulling down another 12 units. What's happening here? It's going up 10 units. Still feels like the pull down is creating a little bit more of a negative Y between the two. But once we get here, yeah, 416, that's 32 units. So that's going up by 14. This thing is always dropping by 12, yes? Looks like the upward pull right here from that term is stronger than the downward pull from the other. So how do we find out when that happens? Well, what have you been doing? You've been putting it in graphing form, yes? So let's put it in graphing form. 2x minus 6, 3. Didn't we say around 3? We're starting to get a little upward pull more than a downward pull. And then we put a 0 in 18. So I don't want 18, I want minus 5. And now we have 2x minus 3 squared minus 23. We call that a graphing form. Why is it a graphing form? Well, let's find out. How many terms do I have in that equation? I think just 2. One of them is measuring squared change and doubling, right? And the other is, that's the other, a constant. So does your brain able to put those two things together? Hopefully. Okay, I'm almost done here. I mean, you spend 7 or 8 minutes in high school student. That's about as long as it lasts in a math class. But try to extend your ability to concentrate for just a little longer. So what are these two graphs, when I combine them, going to do? I'm going to get that graph, but it's going to be what? Shifted down by these Y values. So we get that, right? And you've been doing that when you look at, I don't know, what was it, 23? You've been doing that maybe unconsciously, going to 3, negative 23. Right? Just doing it without maybe thinking about why. Right? And there's the issue in mathematics. As soon as you start saying, why did that happen? Then you're really getting into analysis. Now, what happens with the cubic? There's 4 terms. You have to look at a cubic term, a quadratic term, a linear term, and a constant term. Guess what? Things just got a little more complicated again. Okay? But I'm trying to get you to think about rates of change because this is a pre-calculus class, and in calculus, for those of you who are going to study it, you're going to study amounts and rates and amounts. So you got to start thinking about how rates affect algorithms. What's the rate at 0? Let's find out where we're gonna be at 0. So where are we gonna be at 0? If I add all the y values up, where do I put a little red dot or orange dot, whatever I've got here that works? If I added those 4 graphs together, can you give me a location? Yeah, you'd be right if you said that. Because all other 3 graphs have what for y values when x is 0? 0. So it assumes the constant. Can you tell me at what rate it's changing there? Is the constant changing at 0? No, it's the same y value right across. Doesn't matter what x is. Is the cubic changing at x equals 0? The answer is no. It is not changing appreciably. It is pretty flat. We've been having 4 discussions as to why the change of concavity occurs there. Whether or not you're able to maintain your focus long enough, that's your challenge as a student. Okay, why is it not changing there? Because when you cube something like 0.01, it doesn't change at all. Very minute change versus when you cube 5.01 and compare it to 5 cubed, significant change. So the cubic doesn't add any change to the equation at that green dot. How about the quadratic? When you square 0.01, it's also flat. Y equals x squared is flat at 0. Where's the change coming from? The linear function. So it's going down at that rate. But eventually, the linear is pulling in this direction. Both of the other 2, the quadratic and the cubic, begin to do what slowly? Begin to pull back the other way. Right? Now remember, the flag's going this way. And now you got 2 people on the other side of the rope pull. So what's eventually going to happen to this flag that's going in this direction? It's going to stop because the pullers on this side are getting stronger and stronger. So the question is, when will the flag start coming back in the other direction? When the 2 rates, the rate of this function and the rate of this function, offset the pull down. That's what's going to happen. Okay, let's make a connection. Let's look at y equals 2x cubed plus, I don't know, how about 12x squared minus 8x minus 5? That might be an example of what you're looking at. So if I was going to graph that, I know some things already. I know goes through -5. I know it's going down at 8 to 1. Eventually it comes back up. Eventually it comes back down, which means I've got some kind of graph like that. Where does it max? Where does it min? Well, the only thing on the internet would be calculus, but we're going to do it from a non-calculus perspective. We'll see where it takes us. All right. So back to where we were, almost done talking. This was x minus 2, x minus 10. Point of inflection occurs at 4. That is a magic moment. Then we have to learn why. Does anybody know how I get the number 4 yet? Because I don't know if you realize this or not, but if I wrote ax plus b and I took a out and factored, seems like I'm getting a fairly interesting value here that should grab your attention. Of course, the quadratic is ax minus b over 2a squared. That seems really important. Yeah. And what did we say minus b over a is? That's the x-intercept. What is minus b over 2a? That's the average of the 2 x-intercepts. Where do we think the cubic's going to go? Anybody want to tell me? Very good. I'll write that up on your final exam comment on your final progress report. And I'll say you chimed in correctly with probably the most important statement that we said all term long. So yeah, time out for appreciation, yes. Minus B over A is the average of the roots. Guess what minus B over 2A is? The average of the roots. Guess what minus B over 3A is? The average of the roots. So what were the roots? 0 and 2 and 10. And if you divide that by 3, what do you get? 4. Yeah. And so the rest of this, let's see, plus, I'll put a little bracket around that. This is called H. This is called H. This is called K. And how many terms do I now have? 1, 2, 3, which means I now have simply a quadratic and a linear. And what happens? The constant, we just move it up or down from the y-axis. What's the interplay of this going to look like? And you'll be able to graph cubics. All right, so now, skill development. The rest of the class is going to be skill development. There's 3 things you do in math. You evaluate, you solve, and you graph. And I think our graphing has taken a back seat so far in this course. It's now getting the front seat. So we're going to learn something hopefully today about skill development. That's the bigger topic than just the skills we're going to look at. Do you think you're going to acquire skills in either a job or another course? Then it might be useful to look at the steps you take in skill development so that the skills you want to develop actually suit your needs. I have a hard time watching soccer players when it comes to skill development because I see them running around a track. I see them jogging. I see them sprinting. I see them lifting. I have never seen a soccer player pass a ball by picking up a dumbbell and pressing it. Never seen it. I've never seen anybody, well, they do clock how far people run in soccer, right? But I don't think they just run. Occasionally they touch the ball. So I had an international coach way back when, very lucky because soccer was very new to the country. And the first thing he said to us, he said, if you want to show me how fast you are, we have a track team. If you want to show me how far you can run, we have a cross country team. If you want to show me what you can do with a ball, you're in the right place. Well, developing skill with a ball, like many of the sports, requires skill development. So let's break down some skill development here. Let's see if we can graph a logarithm the 5th time we do it and see if we can gain some perspective on skill development. This should have been stopped a long time ago. All right. End the meeting. There we go. I can do this.